Okay, so first let me give some excuse in some sense for giving this talk, because this is really an old topic and more or less a talk that I could have given 10 years ago. But I was invited last year to give 3 lectures at some symposium given by the London Math Society, and also then invited afterwards to write a survey paper on this, which I then did with Kent. And Kent then thought maybe this could be still a reasonable topic for this workshop. So in some sense it's as much his responsibility as mine for picking this topic. So I hope it won't be too boring. Let me also say that this review paper that we wrote you can find on my webpage, so all the details that I'm skipping sort of here you can just take out from that paper there, and the title is the same as the talk here. So I try to sort of give sort of an overview of certain aspects of this topic of preconditioning systems. And I will sort of try to start very elementary and keep most of the talk at a rather elementary sort of style. So I will talk about Klaus's favorite equation from our lunch discussion. You talked about AX equal B. I think here it's AX equal F, but you know, still close. So we just have a linear system, but for reasons that I hope I can explain, I will really talk about this in an infinite dimensional setting. So it's sort of but just a linear system, and we're just assuming that we have a bounded operator from a Hilbert space into itself, and that it has a bounded inverse, such that we also, of course, have the solution x equal A inverse F, and since A inverse is bounded, this is a well-posed problem, and so on and all that. And I guess I don't have to repeat too much of the conjugate gradient method here. It should be well known to anybody who has any background in numerical analysis. And the basic thing we do, the conjugate gradient method, is like a Galerkin method, but to solve this system, we base the solution on sort of the Krylov space, which is sort of powers generated by spans of powers of the operator. And of course, this conjugate gradient method has this sort of nice convergence property that you can find in any textbook, which say that in the energy norm, it converges with a rate that is bounded by the condition number. So if you have a good condition number, this is what sort of at least gives an upper bound, and for some problems a realistic bound on the convergence rate of the method. And it's just one thing I like to emphasize here, that the method is perfectly well defined in an infinite dimensional setting, because all we have to do is compute powers of the operator, and the only thing that you cannot put sort of more or less automatically on the computer is how to apply the operator A to something. And of course, if the dimension is big, it's more computations to do that, and if it's infinite dimensional, maybe you cannot do it on the computer, but you can think that you can do it. And this is what I want you to think for this talk here. If we have systems that are not positive definite, such that we cannot use the conjugate gradient method, but if we still have that A is bounded and it's an isomorphism such that A inverse also exists, then you can do the same thing with the minimum residual method. So you just go away from symmetry, but still you can use exactly a similar kind of method. And also for this one, you get short recurrence relation. So the basic assumption for this is you need the operator to be symmetric. And so in most of my examples, I will consider symmetric systems. So I will be in this situation that if I have a system that are well conditioned, then I can always think that I can solve it by any of these iterative methods. So this is how sort of I just want to bring in the condition number, so I don't want to talk more about these methods, you can use conjugate gradient, you can use the minimal residual, or maybe the conjugate gradient to the normal equations if you like. All the time the convergence just will be bounded by the condition number. So from now on we only have to think about condition numbers. Okay? Okay, so let's take a very simple examples, not a PDE, but an integral equation. Sort of well known in textbooks in math as an integral equation of a second kind. So you want to find a function u such that u plus some integral operator is equal to a given right-hand side f. Then it's sort of the classical theory of Fredholm operators apply, such that if this operator is 1, 1, as an operator from L2 to L2, it would have a bounded inverse, and we will be in a situation where this theory fits. So if it's symmetric, we can use conjugate gradient to solve this equation. If it's positive definite, excuse me, we can use conjugate gradient. If it's not positive definite, we can use the minimal residual, and everything sort of fits. So it's a good example. Of course, to evaluate this operator, we have to compute integrals. So, you know, that might be maybe hard on the computer, but this is more for illustration. Just think we can do it. So if we can do it, then we can solve infinite dimensional system. That's sort of all I want to tell you. Okay. Example number 2 is, of course, to go from integral equation to PDEs, and our favorite equation is the Poisson equation, the good model for everything or the bad model for everything. So let's try to do the same thing. So we all know, at least if we take in finite element courses and so on, we can think about this as an operator equation where the operator A goes from, let's say, H01 if we have Dirichlet boundary condition to H minus 1. So let's try to think the same thing. I mean, you should have in mind here that these iterative methods, like the conjugate gradient method, is what we're using all the time for discrete system. What does it do if we try to do it on the continuous system itself? Reasonable thought, I think. So what happened? Well, you remember what we do in this Krylov space method is we take powers of the operator. And from what we learned about the space H01, that's a subspace of L2, and that maps us into H minus 1, which is a larger space in L2. So the situation looks basically like this. I start in a small space, the operator maps me into a much bigger space, and then you see at once you don't have a chance of using these methods, because after one iteration you're outside the domain of the operator, and you don't know how to continue. Right? So the conclusion is that in some sense the method that we use all the time for discrete system is not even well defined for the continuous system itself that we really try to approach when we do refinement of the mesh and so on. Okay, so that's our solution. Krylov's best method for these problems are not well defined. Okay, so what should you do? So typically, for many problems, we will exactly be in this situation that we have a system, at least if we restrict ourselves to linear problems now, that we have a problem that we formally can write as AX equal to F. Here X is the unknown solution, F is the right-hand side. But we have this situation, since we're talking about differential operator, that it takes functions with some smoothness and you map it into functions with less smoothness. So you are exactly in this situation that you map from X into some space that we may identify as a dual space, which is a larger space. Okay? And then we are exactly in this situation that we cannot continue. So what is the solution? The solution is very simple. Basically what you do is, since you mapped yourself up to this big space, what you need is an operator that goes back. And this operator that goes back is exactly what we will refer to as a preconditioner in this setting. Okay, such that when we look at the precondition system, that's going to have the operator A composed with B, is that first we apply A and go out to the big space, and then the preconditioner takes us back. Sort of very intuitively, and